So I want to talk a little bit about HPC, but the big topic will be performance optimization. As Eric said, our HPC systems are very much like these data centers, a big hall full of computers, cost not as much as the Google and Facebook centers because we don't get so much public funding to make these very big ones. But so what's the difference? I think the difference is that we basically have users who want to run one application, say climate modeling, and they need as much compute power as possible. So we take the whole machine, put that one application on it, and try to run it as fast as possible. Because they never have enough power, they went to all this effort our last speakers did, said operating system. Oh, I don't need an operating system. Get rid of it. Yeah, I put just a microkernel on it. I run one core on every thread or core or hardware thread core. So I don't need a scheduler. I do user level communication because I'm the only one, so I don't need protection against other stuff. So get rid of everything which is in the way to get as fast as possible. And people are always, as I said, the performance, and it's working in this field for 20 years. It's like Formula One. Yeah, you always want to beat the others, you want to be faster, and so on. The problem is this systems got bigger and bigger, and multi-core has a big role into it, and I will tell you more about it. So the problem is always how to make, you have this big system, it costs a lot of money, but how to make sure it's really used. Yeah, and this is where my team comes in. So we are national and a European computing center. So application people, which are from, by their main profession, are physicists or chemistry or biologists, they program the computers and they come to us and say, hey, it's not running fast enough. I need my results faster. And this is why I come in, and then we come in and my team and our tools try to help the people, try to nail down what's went wrong, and do it. And this is the talk about how to do this. If you have this huge computer, a huge application, it's not fast enough, what can you do about it? I just, in the break, I added this slide because I thought it might be actually interesting here for this context, because we talked about multi-core, and the first speaker said, basically mobile, you don't need more, it's 2 or 4. The others didn't mention so much the multi-cores. I thought at least one person who gives the talk has to talk about multi-cores. So what we do in the top 500, we want to brag about our system. So every half year, we make a list of the most powerful data center or HPC centers which are used, and we call it the top 500. And then I can go there, see this is 500 system listed in the last list, which was June 500, and how many of them used as a socket, like 8 cores, 12 cores, and so on, and you see the percentages. So basically, the smallest one we have, so it's 4, yes, there's nothing below before, but just a few percent. 10 is 6. But a lot of them are actually using VO. So we really are using multi-cores because, as I said, we can't get enough compute powers out of it. So the more cores we have, the better is it for us. So how does an HPC system look like on an architecture level? It's basically you have a set of nodes, and it's connected by a network. And this is how it started 15 years or 20 years ago. You just had single processors, and you connected them together. Meanwhile, of course, it's a little bit more complicated. Each of the nodes is basically a little shared memory node, which has multiple sockets. These are the P ones. And because this is not enough, we add GPUs or other accelerators. And again, there can be multiple of them. And so you would actually have a parallel system out of parallel system. And meanwhile, and then it can be in different organizations, like more NUMA-oriented or SMP-oriented. But the funny thing is now each of the sockets are multi-cores. So each of our general-purpose processors is a 4-core, 8-core, 12-core, 16-core. And of course, you know the accelerators, which are little, like a GPU, is nothing but like another parallel system. So the systems we are dealing with is a parallel system out of parallel system out of parallel systems. Data spread it all over from the registers to different level of caches, shared and non-shared between different things. And then, as I said, now we're talking about putting SSDs in each node. So we have local data and then the global data and so on. And then the network is not just like a simple switch, but we have trees, fat trees, dragonflies, torus. So our blue gene, what we have in Jülich is as a 5D torus. I can even visualize how it looks like. So this is basically the hardware we get. And now people say, okay, now you just write a program with 1 million threads and make it efficiently run on the system. So that's basically the problem what we have. So this is just what I said, just written up. So we have these HPC system, complex configurations, huge number of components, more and more heterogeneous, never enough memory, and now because of a large number, in order to save power, so you get running the cores at different speeds, and because of a huge number, a lot of components fail, so you replace them on the fly. So the whole thing is even dynamically changing. So you try to somehow cover that in the software, and then as at the end it isn't working, people come to me and say why it's not working. And as I said, we need now very powerful tools to be able to handle that. But I thought, yeah, I mean, I'm talking about this huge system, but is some of the stuff I'm talking actually also interesting in like a more traditional system, like a mobile or embedded or smaller system? And I think there's actually not too much difference. The only difference is basically the huge. Yeah? When you have a mobile phone, you have one processor in it or not 10,000, but it's heterogeneous. Yeah? You learned, yeah, you have 4 big cores, 4 small cores, you have a GPU with multiple cores, you have DSPs for video processing, for audio processing. So it's a very, very heterogeneous system, and you have to program that. And again, we want to save power, so it's dynamically changing. And so it's the same. The only difference is basically perhaps the huge thing. And I can come back to the end there is some things how HPC connects to these systems. Okay, so for tools, yeah, what do I have to handle? The extreme concurrency. Yeah, so I mean, if I have 1 million cores, I need to measure the data on it for 1 million cores and have to handle that and analyze it and show it to the user. Heterogeneity gets more and more complicated. It's easier to handle 1 million of the same thing, about like 500 of these and 20 million of that and so on. The third problem we always have is, of course, I could put as much sensors in, get a lot of data out to really understand what's going wrong, but the more sensors I put into the software or something, the more I change the software. Yeah? And so I'm not measuring the original application anymore, but I'm measuring this instrumented thing with a lot of, which is not very helpful. So what we always have to balance is just put enough sensors in and get enough data that we can find the source of our problem without disturbing or to perturbate the original application too much. And then what the speaker from ADAPT talk also said, I mean, getting all this measurement out, how much time I spend here, how often this gets called, how many messages I send is interesting, but it doesn't tell me what's wrong with my program. So I need insight. Insight is very important. And the more complex and integrated the systems get, the more bigger problems we have to getting really good information sources. Okay, so these tools you want to use are, as I said, they have to be scalable, they have to be insightful, they also have to be portable. The thing is, my organization, we get typically a new cluster every 3 to 6 months. There's a new little prototype, people playing around with it, so all the time. So I can't really rebuild my whole tool infrastructure all the time. So I have to have something which is working almost everywhere. And integrated means, I say that later. And then of course it has to be, yeah, when you want to sell it to other people, they want to rely on, if they basically get your tool, use it, learn how to use it, that in 3-4 years it's still maintained. And it's, yeah, of course, so maintained and versatile is important. And what I want to talk now, and the rest of my talk is about these portable, insightful, scalable, and integrated. Okay, so Eric mentioned that there's a few people out there who do this for, say, the last 20 years. They do it mostly, not all of them, but a lot of them are open source. And they work on different systems. So these are a few of the tools in the HPC space which I basically used myself, and I know they can working. There's a few company tools like Cray, Intel has a lot of them, but often they only work on their system, so they don't work in the, like the portable portion is failing. Yeah. Okay, portability. So this is basically a list what my tool, which is called Scalasca, and I will introduce in a minute, is currently running on. So we are running basically on every Cray architecture Cray brought out in the last 10 years, on a different blue gene from IBM. We are working on the K machine in Japan, and on the commercial side of it with the Fujitsu FX10 100. We're working on a Chinese system, Tihanyu 1A and 2, on Intel mic-based system, and then basically all kind of Linux clusters, be it A32, 64, PowerPC, Power, whatever, and all kind of Unix-like operating systems. This is currently what we support, and it's actually not too bad. So this is what you have to support basically from a tools perspective. Yeah? So the good thing is the operating system got simpler because almost everyone is using Linux now. Of course, on the big clusters, you have some microkernels, but they still give you like a Linux-like interface. And there's a few systems still out there which using AIX, and Fujitsu has their own, but the rest of it now all switched to Linux. So this made it a little bit easier. The HPC applications are typically written in C, C++, and Fortran. And here it gets a little bit more complicated. So we're currently supporting at least 6 to 7 different versions of compilers. And this is important because there's OpenMP. This is a pragma-based way of doing multi-threading. Because it's in the compilers and we want to know about parallelization, we need to support them. And so we have to support all these different compilers which support different versions of OpenMP and in different ways, and our tool has to handle that. And the same thing, MPI. MPI is the standard, basically, all HPC applications are using for exchanging messages and synchronizing between nodes. It stands for Message Passing Interface. But again, it's a standard, but there's multiple implementations. There's MPI, OpenMP, with different vendors are on. And again, we have to handle the different versions supporting different versions of MPI. It's doable, but a lot of our efforts is spent on just making configuration work, handling the different versions, and so on. Okay, insightfulness. So that mostly what people know about tools is, okay, you measure that, how much time is in different different portions of my code, and you get these profiles, everyone knows, and then you see these histograms and part charts, yeah, like 20% is spent here, and so on. Of course, you can a little bit go further. We want to not just see the distribution of a whole program, but we want to see how the behavior changes over time. So we typically use these timeline tools. So you have basically a line for every processor or thread going from left to right. Time goes from here to here. And then you use different colors to indicate what that program is currently doing. When they are sending messages or synchronizing, you draw lines. And so you can see basically very quickly, like over time, how the program is behaving. And it works, of course, very nicely. You have like a small example. So like this is what I tell people right in an exercise. Send a message. You have 16 processors, and the first one sends a message to the next one. He sends it further, and so the message gets sent around in a ring, and so you can nicely see what's going on. But of course, this doesn't work if you go to a real application. This is just like 64 processes, and then we see all the black lines are messages. Every purple thing is a synchronization, and then these tools allow you to basically zoom in, say, okay, this is portions entering, I look enter, but then you basically zoom, and you will find more and more of these messages and so on. And so there's a lot of people out there who basically try to sell you these timeline tools, and the bad thing is what they only show you basically this side. Say, okay, here you see very quickly, yeah, and this is right if you found that, but the problem is in the beginning you see this big thing and you have to find this little thing inside all of these large space. So this is, yeah. So basically there's all these tools out there, and they have additional windows, and each of them has a context menu. Say, oh, now basically don't show me this, but this way. And so you have hundreds of pictures with hundreds of options, and you quickly get lost. So this is how my team came in and said, okay, this is basically, yeah, like one of these situations these people show you. Oops, what do you think did I press here? Okay. Yeah, you have processors, everyone is working on this yellow part, and then basically that one is sending a message down to here, or you see that this is releasing a lock, and this is basically he was trying to acquire it. So basically, because that guy didn't have enough to do, that portion here was kind of lost. And so this is actually a source of a problem. So what we said, okay, we meanwhile, after a few years, like especially for this message passing interface, we know all these situations, yeah, and we just basically make a catalog of all these problems. We give them a name. This one we call late sender, and for each of them, basically we say how you can detect it in these timelines, and then we have an automatic program going through you, and basically at the end it just tells you, yeah, we found 1 million of these late senders on this spot, and because we know how much you lost, this is how much you lost. And so you don't have to wait for it, and this is basically what we did in our tool. Yeah, and this is some of the situation we detect. Like this is this late sender, but it also the same thing is for locking. You have this like multiple processes, synchronizations. You can do things like, oh, I'm waiting for the wrong message, or if I would have waited for that one first instead of the other, it would be replaced and would have been better. And that's, as I said, we can do the same thing for threading, for locking, and we just basically have these detector, which basically takes the traces, goes through it, and tells you how much it is. The problem is only, yeah, if I have basically all this data on my laptop and I do this pattern search, it's quite simple. But what do you do if you have the data and you basically collect it on every processor, on all the different nodes? So you have basically on 100,000 nodes, you have the data, but it's now distributed, and now you have to do this pattern search in parallel. And this is basically what our tool does, basically. So we are able to instrument the code, get all the data, when we are sending messages and so on. And then basically, when the program is ending, we are reusing the parallel partition, the parallel partition the program is running on, and doing this parallel analysis. So one is this wait state analysis I just told you, but also we do root cause analysis, I tell you in a minute what it is, and critical paths and so on. And this is basically how it looks like. So I have here the different metrics, yeah, like time, how often you do something, how synchronizations, and either it's in seconds or in numbers, and I can click on it, say like here I'm interested, yeah, these seconds on late sender, where do they occur in my program? So I click on it, and then I see the source code, I see the call tree, and I see where it happens, and then I see the distribution. And in order to allow you to find large numbers, or we use this color scale, so basically in front of every number is this little box, and so you just look for more reddish thing, and so you quickly find things which are very high and where they are very quickly. And so this basically says, okay, we found this, you're waiting for messages at this specific MPI call, at this stage in your program, and this is how it's distributed over all your processes and so on. This worked very well 15 years ago, where you had here like 64, but of course now with 1 million or so, it's no longer working. So what we switched over is using topologies. So either we're using the hardware topology, you know, like the processors are arranged in 2 or 3D meshes, or even now, basically, we are using scientific applications. They often have an application topology. So here you see an example. This is the community Earth system model. So this is one of the climate applications where they simulate the simulation of ice. And of course, then basically how they do is they use the Earth surface divided up in pieces, and then the different processors work on the different pieces. Yeah? And so now I can record that, which processor is working on that, and now I can see basically processors, yeah, like this waiting on the messages here, basically where did it occur, and it's kind of clear because it's actually inside some calculation on the ice simulation here. Yeah, so there's not much ice in the equator, so these processors have nothing to do, and of course the weighting here is especially high. Yeah, this is, the tool can show you, but I guess no tool developer needs a tool to tell him that there's no ice at the equator and so on. This is actually, it's nice to know when you are losing time blocked for a message or for a lock and so on, but this is actually only a symptom. Yeah, the problem is not that you're waiting, but that there was some stuff happened before which caused you to this imbalance and that you have to wait. So the trick is actually not to find, which is our tool can do this, is nice, where all this blocking and waiting occurs, but it would be much nicer to know where it came from. And this is the next thing we implemented. We call it the root cause analysis. Yeah, you think basically, so you have something. Every processor is working on this foo part, then on the bar part, and then we're exchanging messages. And for some strange reason, we didn't balance the load right, so the foo basically on one processor took longer. Yeah, so our original analysis base said, okay, here you're waiting and here you're waiting. But now what we basically do is we kind of, once we find this pattern, we look backward again and say, where did it come from? So we first can say, okay, this portion of a waiting was actually caused by another waiting, and that one was caused by the delay here. Yeah, so we can go back through all that, and now we can actually basically do the same thing. We add it up, and we can tell you again where that stuff happens. Yeah, so again, so here basically where's the direct stuff waiting? So this is on the border of the ice. Clear, yeah, you wait. The first one who waits on the ones who are working on the ice are next to the ice. The indirect ones are on the equator, and now the big question is, where does the delay come from? Any guess? Yeah, everyone says, okay, it has to be the equator. I mean, this is where there's no ice. But what our tool found, it's no, actually, it's here and here and here and here and here. And what happened is, so there was a bug in the code where when you had complex coastlines, like the Japanese islands, this is our Aleut Islands and other stuff, that they basically delayed that and then basically viscosed it. So by putting all this together, yeah, and this is a code running on, I don't know, I should say somewhere, it was 4,000 cores, yeah. Basically our analysis could quickly pinpoint, yeah, what is the problem, and where does it come from, where's it in the source code, where do you have to fix it, and so on. And so this is the kind of tools we are working on, and we do hope to make it available. Okay, so all of that is nice, and I told you it's very simple if you do it on a small system. Yeah, I have a few hundred ones. I mean, if I have a powerful server with a few gigabytes of memory, I can put all these trace data, all these measurements in one place and just like quickly calculate it. But how do you do that with these huge numbers? Yeah, and just to show you basically this again the top 500, how that changed over the years. So this is basically the 500 most powerful system in the world, which is actually covering quite a lot. And so the smallest system now is in a few thousand. So it's a logarithmic scale I actually had to put in because, and this is where the multicore comes in. Originally, the systems got larger by saying, okay, I'm adding a few more nodes I can afford, yeah, and make it larger. But now, you're adding a few more nodes, but now we're replacing also the single core by dual, the dual by quad, the quad by 8 or 16 and so on. So you get this exponential growing. Yeah? And so I had to put this logarithmic thing. So the largest system now is over, I think it's, let's see, this must be the T-Handium system. I think it's 7 million cores now, and the smaller ones. But yeah, you want to handle a lot of people. But even if you look at the medium or average, you are in the multiple 10,000s your tool has to handle. Yeah, and this is a machine I have at home in my basement, in my organization's basement. It's an IBM Blue Gene, so it's 28 of these boxes, and a total of almost like 500,000 cores, but it's 4-way SMT, so you can run 4 hardware threads on each core, so I can run on this machine 1.8 million hardware threads. And of course, because my team get paid from my home organization, said, okay, yeah, if we pay your tool development, you have to support people on our local machine, and so on. So I tell you at the end basically how far we got. So how do different people, not just our team, handle that? Yeah, the first thing you have to do is you have to make sure that the data you collect, you do it in a scalable way. But in the end, there's one person sitting in front of it, so you have to reduce all this data together to one point. So you have to have a scalable collection and a scalable reduction. The scalable collection is not as bad because, yeah, if every process is collecting the data, so if you're adding more, you automatically add also more collection power and more memory to collect it. But as I said, the reduction is important. So what we basically do is we're using the high-performance communication, like mostly MPI. So at the end, when the program is finished, we hijack MPI, and then we add an additional phase at the end to use the high-performance network to collect the data together. And then we also try to, keep it still separate and collect it in an interesting way. And then all kind of parallel I/O gets used as much as possible. Then you have all this data, and then you have to analyze it to produce some interesting graphs or displays with Voodoo. And then the only way of doing it is basically parallelizing it. Yeah? So one thing is, as we do basically this pattern detection, with delay and critical path analysis are parallel applications. So we have to parallelize that, and we use the full system to get it done as quickly as possible. Vampire is one of these timeline tools, and what they do basically, so they measure the traces on every processor, but leave them there, and then they run basically like a data server in parallel, and then the timeline visualizer you see on your screen is just basically a visual client, but all the calculation, what we draw, is done in parallel by basically working on these traces. And then you have to use all kinds of sort of like 3D topology, hierarchical browsers to make it work. And here's a few examples. So this is tau. So basically here you have all the different functions, here all the different threads, and then you basically, you can select a metric, and basically the height can encode one metric and the color another one, so I can see, like what is executed most and has the most cache misses. And so by using 3D, you can get quite far. So this can easily, like this shows like a 16,000 processor thing. This is the largest timeline visualization I ever did, doing this with this Vampire server, as I said. So they're collecting the data. So in total, they collected about 4.5 terabytes of trace data. And then basically, they ran their data server on 20,000 cores to basically read in all this data and analyze it and send it to the screen. And then on one screen, you still can look at it. And so this is the whole process run. Here, basically, we're looking currently at this little interval, which is shown here. And then, but I can zoom in, and you can still see every messages. But as I said, you have to use a 20,000 core system to make it work. But okay, I understand. This is Scalasca. Again, like a few years ago, on the last machine, where we did 300,000 again. Like to give you, that we measured, but for 10 minutes, and which produced something like 7.6 terabyte of trace data. We had to write it out, read it in again, run our N analysis, which took then, because it's parallelized, just 11 seconds, and then you could look at it. But just give you the numbers how what we have to handle. And this is the current thing we can do. So the largest was basically a real application on our system. And one, basically, we couldn't use only two-way SMT, so we got to almost 1 million processes. We could run it with four-way SMT, but then we could only do it on 20 racks, but it got us to 1.3 million MPI ranks we could analyze. So this is basically, I don't know what, other people don't tell me how far they got, so I claim world record on trace analysis. I haven't heard any larger numbers so far. Okay, and you still can look at it. Yeah, so it's, each of these single pixels is the execution time in a specific way at all, and so it still works. Okay, 5 minutes. Okay, integration. Yeah, so you don't want to have a tool for like analyzing the message behavior, analyzing the threading, analyzing the accelerator usage, but you want to have one tool which can do all of it. You want to ideally use all this data to feed into modeling. Yeah? So the models can be used like real measured data and synchronize them. And as I said, and the tools need to work together. So one thing we worked on is called SCORP, because all these different tools basically have to do the same thing. Yeah? We have to intercept every MPI message, we intercept every thread creation, every task. So everyone has to do the same stuff. You just do different analysis. So all these people got together, and we got funding from the German ministry. This is called SCORP now. This is now a tool, basically, which it's this first part, the instrumentation, measurement, and capturing part. And now a few people share that, so it's a really open source community project. And this is basically what we currently support: MPI, SHMEM, OpenMP, POSIX threads, OpenACC, CUDA, and OpenCL. In any combination, we can generate these profiles, the traces, and then, as I said, on top of it, you put the different tools. So this is, yeah, this is the platforms we support here. Yeah, we come up to, with that system, up to 700,000 cores, and we put a lot of things in by nightly builds, continuous integration to really make sure it's working and so on. And this is basically how it looks like. So we have this SCORP system now. So you either get these Cube4 profiles or OTF traces out of it. You can use our browser, which I just showed you, but also this Tau tool can actually read these profiles. You can, on these traces, you can run our analysis, and the output is actually looks like you still can use the same browser, or you can use the Vampire tool to look at the traces together, and then you can also put it in a database, so you can do multiple, like compare performances over multiple runs. And then there's a tool in Munich called Periscope, which basically not storing the stuff in files and do an offline analysis, but tries to do an online analysis. So this is basically the whole ecosystem around this SCORP. Another interesting thing that they did is, how can this tool work together? So, because we are actually, in our tool, are detecting these places which might be interesting to look at. So, yeah, you bring up our system, says, oh yeah, so please connect me to a trace browser like Vampire. It automatically brings up the Vampire tool. And then you say, okay, here's this late sender problem at this place. You can use the context menu. You say, okay, this is the one I'm interested in. Show me one instance in the trace where it was the worst. And then it sends over a message, and this timeline browser automatically zooms into that spot. And by combining these two tools, you get much quicker. I know. I skipped that one. 2 minutes on use cases. One thing what we handled, where we're kind of proud of, is now the application space gets more complicated, that these HPC people don't run one application code, but they couple them together, like the climate people. Yeah, they have they take a weather prediction, a land model, a watershed, and they couple together to get even further. Yeah, so this is it's called MPMD execution style, and this is what we measured for them. And the problem was no one could handle their stuff, and so finally we had to modify our tool to make it working. And so they finally could see what's going on in the different portions. And it was actually simple things, yeah, like remove a few code blocks they never really used, or they change a few data structures. And then some subcomponents basically were now twice as fast, and the scaling improved like by a whole range. In the beginning, I said, yeah, this is nice about this huge scalable code, but does it also work in different contexts? In around 10 to 13, we had a project called H4H, which actually Eric was also part of it, where we analyzed some of industrial HPC codes with different tools, and we could optimize them quite apart. And the latest highlight, I was hoping to tell you a little bit more about it, was we got the past 2 years a collaboration with the Siemens. You know, Siemens is a large electrical company, and they have all kind of things they sell, and they realize, oh, hey, all these things have multicores in it. And then there's codes in these things which are, yeah, like 500,000 lines of code. The developer got like sent to a different division now multiple times or left the company. And so how to parallelize all that? So they came to us and can we use your tools to help us doing this? And so we basically used our tools, but we had to change our measuring infrastructure. Yeah, we had to support things like Windows thread, ACE threads, Qt threads, or things like to capture the multicore associated task API. But then the rest of the system we could reuse. Unfortunately, yeah, I mean, it's a big company. They don't want to tell you what they're currently working on, which of their products was not so good, and so on. So
at least not on video.
Yeah, this is basically the only slide they gave me. So they made sure you can't see anything here on these screens, and they tell you, yeah, they could use it, but yeah. Okay, so end of the talk. To leave some time for questions.
Okay.
And
okay, thank you. Thank you, Bernd. So I assume the Siemens example you gave at the end is an example where you don't need millions of cores. This is more like 4 cores, that more normal.
4, 8, 12, depending on the system, yeah.
I have first question for you. So while the work that you do can be extremely valuable to an organization, and you can use your compute resources so much better because you can optimize your code. To develop this kind of tools is also a very expensive hobby, right? Because you need access to the machine, right? You have to convince your management that, guys, I'm going to debug my score P tool here on 1 million cores. It's just going to take half a day. I mean, that's an expensive hobby. So do you get access to these machines to develop your tools, or what do you have?
Meanwhile, yes. Yeah, 15 years ago, it was a big issue because, like, you send an application to use compute time on a large public machine, and they said, oh, it's computer science. That's not real science. Yeah? But now they realize, they know how expensive these machines are. They know if these even get 10% out, they can use this 10% save for more people to use the machine, or the existing can be longer. And so every year, my team has accounts on basically all the large machines out there everywhere. And as people like Fujitsu or the Chinese came to us saying, hey, yeah, like here, please, yeah, here's an account, please port your tools over. And or Siemens comes to us. Yeah, so meanwhile, it took a while, but now it's working like this.
Alexandra?
Alexandra Jimboran from Uppsala University. So you were mentioning that you are profiling applications both for shared memory architectures as well for distributed memory architectures. How do the metrics of interest differ between these two?
So for shared memory, it's more the parallelization of shared memory. Yeah, so we basically measure like the task creation, joining task, locks, critical section, and so on. And again, the same thing. Yeah, how much are you blocked for a lock or critical section, or at the end of a parallel, and so on. What we're a little bit bad are is, okay, here's a function which takes a lot of time, but we don't know why, because we can't really look like inside a function. Yeah? It's typically then a memory or calculation. We can collect a few hardware counters to say, okay, yeah, you have too many cache misses in this section and so on, but looking deeper is harder. And here's a connection to other people like the adapt thing, which they have like modeling. They say, okay, now this kernel, yeah, takes too much time. Yeah, can you please, yeah, take that kernel and going through the modeling tools or simulation tools, what the other speaker showed you, and then find out what's going on here in detail. So this is, as I said, our tools can go quite far, but still cannot solve everything. So we're still working with a lot of our people to get into these issues.